Slide 1. Today we are going to make resonance structures way less confusing. Resonance is one of those organic chemistry topics where students usually know it has something to do with arrows and electrons, but they are not sure what is actually allowed to move. The main idea for this whole video is simple. In resonance, the atoms stay in the same place. Only the electrons move. By the end of this video, you should know how to draw valid resonance structures, avoid the common mistakes, and tell which resonance contributor matters the most. Slide 2. First, let's define what resonance structures actually are. Slide 3. Resonance structures are different Lewis structure drawings of the same molecule or ion. The atoms are the same. The atom positions are the same. The total charge is the same. The only thing that changes is the placement of electrons. Usually, that means pi electrons, lone pairs, or charges are being drawn in a different place. A resonance structure is not a new molecule. It is another valid drawing of the same molecule. So when you see the double-headed resonance arrow, do not think the molecule is reacting or changing into a new compound. Think, same molecule, different electron drawing. Slide 4. Now let's fix a common misunderstanding. Resonance does not mean the molecule is switching back and forth really fast. It does not mean atoms are moving around. It is not a reaction mechanism by itself. And it does not mean every random drawing is valid. The better way to think about resonance is this. The real molecule has electrons spread out or delocalized across multiple atoms. The resonance structures are drawings we use to show where those electrons can be placed. Some drawings are better than others because they are more stable. Slide 5. The real molecule is called the resonance hybrid. This means the real structure is like a blend of the valid resonance contributors, but not always an equal blend. The more stable contributor affects the hybrid more. This is why resonance can explain partial bonds and partial charges. A key exam phrase is, delocalized electrons stabilize the molecule. Slide 6. Now for the most important rule, only electrons move. Do not move atoms. Do not change the order of atoms. Do not break normal sigma bonds. The atom skeleton stays fixed. The only things that can move are electrons, usually lone pairs or pi electrons. Before you submit any resonance answer, ask yourself, did I move electrons or did I accidentally move atoms? Slide 7. Next question, which electrons can move? Usually, resonance happens when you have conjugation. Conjugation means you have overlapping p orbitals that allow electrons to spread out. Look for these common patterns. A pi bond next to another pi bond, a lone pair next to a pi bond, a pi bond next to a positive charge, or a lone pair next to a positive charge. The key word is conjugation. If the orbitals cannot overlap, resonance usually cannot happen. Slide 8. Curved arrows show where electrons move. The tail of the arrow starts where the electrons are right now. The head of the arrow points to where the electrons are going. If a lone pair becomes a pi bond, the arrow starts at the lone pair and points between the atoms where the new pi bond forms. If a pi bond becomes a lone pair, the arrow starts at the pi bond and points to the atom receiving the electrons. A common mistake is starting the arrow from an atom label. Arrows do not start at atoms. They start at electrons. Always ask, where are the electrons now and where are they going? Slide 9. Formal charge helps check whether the resonance drawing makes sense. Formal charge equals valence electrons minus non-bonding electrons minus 1/2 of bonding electrons. You do not always need to fully calculate it every time, but you do need to understand what it checks. Formal charge tells you where positive and negative charge is located. In resonance, the total charge must stay the same in every structure. So if you start with a -1 ion, every valid resonance structure must still have a total charge of -1. If the total charge changes, the resonance structure is wrong. Slide 10. Here are some formal charge patterns that show up all the time. Oxygen with 1 bond and 3 lone pairs usually has a -1 charge. Oxygen with 2 bonds and 2 lone pairs is usually neutral. Nitrogen with 4 bonds is usually +1. Carbon with 3 bonds and no lone pair can often be +1. These patterns help you quickly track where charge moved. Slide 11. Now let's talk about major and minor resonance contributors. Not every resonance structure matters equally. The major contributor is usually the most stable drawing. A strong contributor usually has full octets, fewer formal charges, negative charge on electronegative atoms, and less charge separation. A weak contributor may have incomplete octets, extra charges, bad charge placement, or too much charge separation. A good quick rule is full octets first, then fewer charges, then better charge placement. Slide 12. Let's look at acetate. In acetate, the negative charge can be shared between two oxygen atoms. On one structure, one oxygen has the negative charge, and the other oxygen has the double bond to carbon. The lone pair on the negative oxygen can move in to form a pi bond. Then the existing carbon-oxygen pi bond moves on to the other oxygen. Now the double bond is on the other side, and the negative charge is on the other oxygen. These two contributors are equivalent because both oxygens are the same. Both structures have full octets. Both have the same number of formal charges. And the negative charge is on oxygen in both drawings. So for acetate, both resonance contributors matter equally. Slide 13. Next is the allylic carbocation. An allylic carbocation is a positive charge next to a pi bond. The pi bond can shift, and the positive charge can move to the other end of the system. The atoms are not moving. The electrons in the pi bond are moving. This is why allylic carbocations are more stable than isolated carbocations. The positive charge is not stuck on one carbon. It is delocalized. Exam sentence: the positive charge is stabilized by resonance. Slide 14. Benzene is a classic resonance example. You may see benzene drawn with alternating single and double bonds. Then the double bonds switch positions in the second drawing. But the real benzene molecule is not switching back and forth. The real molecule is the resonance hybrid. All 6 pi electrons are delocalized around the ring. That is why benzene has equal carbon-carbon bond lengths, not 3 short double bonds and 3 long single bonds. Slide 15. Now let's look at carbonyl resonance. A carbonyl is a carbon-oxygen double bond. Oxygen is more electronegative than carbon, so oxygen pulls electron density toward itself. One resonance drawing shows a normal neutral carbonyl. Another drawing shows the pi electrons moved onto oxygen, giving oxygen a negative charge and carbon a positive charge. This charge structure is usually a minor contributor because it has charge separation, but it is useful because it explains why the carbonyl carbon is electrophilic. In simple terms, the carbonyl carbon is electron poor, so nucleophiles like to attack it. Slide 16. Amide resonance is another important pattern. In an amide, nitrogen has a lone pair next to a carbonyl. That lone pair can donate into the carbonyl system. The nitrogen lone pair forms a pi bond to the carbonyl carbon, and the carbon-oxygen pi bond moves onto oxygen. Because of this resonance, the carbon-nitrogen bond has partial double bond character. That is why amides are flatter and less basic than normal amines. The nitrogen lone pair is partly involved in resonance, so it is not fully available to grab a proton. Slide 17. Next is enolate resonance. An enolate has a negative charge that can be shared between an alpha carbon and an oxygen. In one contributor, the negative charge is on carbon. In the other contributor, the negative charge is on oxygen. The oxygen contributor is usually the major contributor because oxygen is more electronegative than carbon. Oxygen is better at holding negative charge. Slide 18. Now the nitro group. A nitro group usually has nitrogen with a positive charge and one oxygen with a negative charge. The negative oxygen can switch sides through resonance, but the total charge stays the same. One oxygen is single bonded and negative. The other oxygen is double bonded. In the other resonance structure, they switch roles. For nitro groups, remember, keep nitrogen positive, keep one oxygen negative, and let the oxygen positions switch. Slide 19. Here is a repeatable method for resonance problems. Step 1. Draw the correct Lewis structure. Step 2. Find the movable electrons. Look for lone pairs, pi bonds, and charges. Step 3. Check for conjugation. Step 4. Draw curved arrows from electrons to where the electrons go. Step 5. Check octets. Step 6. Check formal charges. Step 7. Decide which contributor is major. After drawing each form, ask, are the atoms the same? Is the total charge the same? Are the octets valid? Are the formal charges correct? If one of those checks fails, The resonance structure is not valid. Slide 20. Now let's go through common mistakes. The first big mistake is giving carbon 5 bonds. Carbon cannot have 5 bonds in normal organic chemistry resonance problems. Another mistake is moving atoms. If the atoms change places, it is not resonance. Other mistakes include breaking sigma bonds, changing the total charge, creating impossible octets, or putting charges in places that do not match the electrons. A good rule is, if the atom skeleton changes, it is probably not resonance. If the total charge changes, it is wrong. If carbon has 5 bonds, it is wrong. Slide 21. Before submitting your answer, run this checklist. Did I move atoms instead of electrons? Did I break a sigma bond? Did I change the total charge? Did I give carbon 5 bonds? Did my curved arrows start from electrons? Did I forget formal charges? Did I assume every contributor is equal without checking stability? This checklist catches most resonance mistakes. Slide 22. On quizzes and exams, resonance usually appears in a few common ways. You may be asked to draw all resonance forms, find the major contributor, draw curved arrows, spot the invalid structure, rank stability, or predict where charge can move. Most resonance questions are rule-checking questions in disguise. When you get stuck, start by finding pi bonds, lone pairs, formal charges, and nearby empty orbitals. Slide 23. Now try this practice question. We are starting with an acetate type structure. One oxygen has a negative charge. The other oxygen has a double bond to carbon. Your job is to draw the missing resonance form. Pause the video here and try it. Check 3 things: same atoms, same total charge, full octets. The lone pair on the negative oxygen can move toward the carbon to form a pi bond. But if that happens, the carbon-oxygen pi bond has to move on to the other oxygen. Slide 24. Here is the solution. The negative oxygen donates a lone pair to form a carbon-oxygen pi bond. At the same time, the existing carbon-oxygen pi bond moves on to the other oxygen. Now the double bond is on the other side, and the negative charge is on the other oxygen. These 2 acetate contributors are equivalent because both have full octets. Both have 1 negative charge, and both place the negative charge on oxygen. Slide 25. Let's recap. Resonance structures are different valid drawings of the same molecule or ion. Only electrons move. Atoms stay fixed. Sigma bonds usually stay fixed. The total charge stays the same. Curved arrows start at electrons and point where electrons go. Formal charge helps you check your work. The best resonance contributors usually have full octets, fewer charges, and better charge placement. And the real molecule is the resonance hybrid. Final rule: draw valid structures first, then decide which ones matter most. That is resonance structures made simple.